Welcome back, everybody. So last time we put our full motto of calculus to work and computed our first bona fide definite integral. And by bona fide, I mean we needed the motto of calculus, right? It wasn't a nice geometric shape or anything like that. We figured out a way to write an n rectangle Riemann sum. And through a whole bunch of work working with that, we were able to mess with the way that looked, take the limit as n went to infinity, got our final answer of 4 square units for that area. So today, we're going to see how summation notation can streamline our work and what we're writing. There's a little bit of groundwork we have to go through, though, getting a feel for how summation notation works. Once we get our feet wet with summation notation, we'll take a second look at our integral from last time and work through the exact same one, this time using summation notation. All right, well, let's start in. So here we have the sum from I equals 1 to 25 of 3. And so the sum from I equals 1 to 25 is telling us that we're going to have 25 things added up, right? And this thing out to the right is telling us what's going to be in each term, right? So for I equals 1, we're going to have 3. For I equals 2, we're going to have 3. And for I equals 3, I equals 4, all the way up to I equals 25, we're going to have 3. All right, and so we actually have, 25 3's added up. And so, all right, just thinking about how multiplication works, this is going to be 25 times 3, or 75, as that result. And now here, from this kind of specific computation, I think we can capture a general formula here. Well, if we're just adding up a constant a certain number of times, well, then the result is just going to be the number of times our constant. All right, and so we can write that in a nice general form over here. All right, sum from I equals 1 to n of some constant is just going to be that n times our constant. All right, and so with this formula, we know how summation notation works with constants. All right, if we're just summing a constant. Well, now let's think about constant multiples. All right, here we have this I squared that's being multiplied by 3. And we're summing up from I equals 1 to 25. So again, we're going to have 25 terms that we're adding up. All right, and to figure out what is in each term, we just take these i's that we are at and plop them in, like with a function, wherever we see an I over here. All right, so for I equals 1, we're going to see 3 1 squared. For I equals 2, it's going to be 3 times 2 squared. For I equals 3, it'd be 3 times 3 squared, all the way up to 3 times 25 squared for our I equals 25 term. Now, one thing you might notice is that each one of these terms has a 3. All right, and so if we wanted to, we could take these 3's and pull them out front. All right, what we're left with is just the 1 squared plus 2 squared up through 25 squared. All right, this sum here over on the right, if we wanted, we could write with summation notation. Right, is the sum from I equals 1 to 25 of I squared. All right, with that 3 times out front. And so if we look from the start to the finish here, what happened to this 3? Well, this 3 just kind of slid out front of the sum. All right, and so this kind of constant multiple sliding property that we've gotten used to with derivatives and more recently with integrals, it shows up in sums as well, which is real nice. All right, so written generally, we have the following. If we are summing from I equals 1 to n of some constant times something that involves I, perhaps, this a sub I, Well, then we can take that constant and slide it out front, right? And all this is pulling out constant multiple. All right, for our third situation I'd like to think about is how does summation notation work with sums? If we have something involving I and something involving I, well, summing from I equals 1 to 3, right, means we're going to have 3 terms. And in the first term, we're going to have A1 plus B1. Second term, we'll have A2 plus B2. The third term, we'll have A3 plus B3. There it is. It's literally what this sum means. If we want to, we could rearrange all the A's together, all the B's together, write it like this. And now over here on the left, if we want, we can write this as a sum, right, of the AI's. And over here on the right, we can write this as the sum of the BI's. Right, so sum from I equals 1 to 3 of AI plus the sum from I equals 1 to 3 of BI. And notice what's happened from the very start to the end here is that our summation has somehow distributed, right, to both these pieces. Right? And again, this is the property we're familiar with, is breaking up over sums that we've gotten used to with derivatives and seen that integrals have this as well. It turns out sums share the same property, that they distribute nicely over addition and subtraction too. So I'll just add here, or minus, right? If it was AI minus BI, we could distribute and it'd just be the sum minus the sum over on the right. So with those 3 formulas, we understand how summation works with constants, constant multiples, and with sums and differences, and I claim that this gives us a lot of power. Before we dive into our integral computation, let's just do a specific kind of for fun computation and get a little better feel for summation notation. So let's compute the sum from I equals 1 to 15 of 7 plus I over 2. All right, and the idea here is that we don't want to start writing out all 15 terms of this. We want to work with the summation notation. A helpful formula in our work is right over here. The sum from I equals 1 to n of I is n times n plus 1 over 2. And so let's take a minute, pause the video, and see if you can work with these summation formulas to try and get this into a form that we know how to handle and use our formulas. I'll get us started. One thing we might notice is that what we're summing up, kind of at top level, is a sum of 2 things, right? Well, with our third property we looked at, we know how summation notation works with sums. We can distribute it, right? Well, let's start there. Pause the video, see if you can work through the rest and get an actual number as the result of this sum. All right, well, let's talk about this together. All right, if we take our sum and distribute it to both pieces here, the 7 and the I over 2, here's what we get. I have taken the liberty over on the right of taking our 2 in the denominator and sliding it out as a 1/2 constant multiple. Right? But now with our constant multiple rule for sums, we can slide that out front. Right, what we get is the sum from I equals 1 to 15 of 7 plus 1/2 times the sum from 1 to 15 of I. And this is a great place to be because over on the left, this is a sum of a constant. We know how those work from our first rule above. And over here on the right, we have a sum of I. And we know how those work from our formula that was handed to us. Right? So we can use that here. right? Adding up 7 15 times is going to give us 15 times 7. And over here, the sum of I, right? We just need to know the n that we're stopping at to use this formula. And for us, that's going to be 15. So this is going to be able to be swapped out with 15 times 15 plus 1 over 2. So we get the following. So 15 times 7 plus a half, 15 times 16 over 2. And we can work this out. 15 times 7, right? Well, 10 times 7 is 70, plus 5 times 7, which is 35. And then over here, we get 2 times 2 in the denominator. That'll cancel with the 16, leaving just a 4. 4 times 15 is 60. Putting that together, 165 is the result of the sum that we have written in summation notation here. All right. So now that we have a bit of a feel for how summation notation works, let's apply it to our integral from last time. All right, once again, let's compute our integral from 0 to 2 of x cubed as a limit of Riemann sums, right, using right endpoints for valuation points, as we did before. But this time, let's use summation notation, and right up front, let's just hand ourselves the formula for the sum of I cubed that we'll need to use at some point. All right, so starting in, right, our definition of this integral as a limit of Riemann sums is that this is the limit as n goes to infinity of our n rectangle Riemann sum, which written in summation notation looks like this. Right, the sum from I equals 1 to n, since we have n rectangles, and each one of those rectangles' areas just uses the width, delta x, times the height, which we get from our function evaluated at our evaluation point. Right, and the ith evaluation point is what we call xi star. All right, so here we see, to continue working, we just need to figure out our delta x and our xi star. So to start with that, let's draw a little number line over the interval that we are integrating, 0 to 2. And let's first think about delta x. With n rectangles, and our formula for delta x is, again, b minus a over n. So our b is 2, our a is 0. So 2 over n is what we get for our delta x, our width of each of our rectangles. All right, so we know delta x is 2 over n. Next, we need to find our ith evaluation point. And really, this comes from just the pattern that our evaluation points have. All right, so let's start there. All right, the idea is, well, if our first rectangle, right, has a width of 2 over n, and so the first right endpoint we get from our rectangles is going to happen at 2 over n. Right, so that's our x1 star. Our second rectangle also has a width of 2 over n. Right, so its right endpoint, well, since we went over 2 over n's, we get 2 times 2 over n. And for our third rectangle, well, we're going to move over another 2 over n, and its right endpoint is going to happen at 3 times 2 over n. And so at this point, we can kind of see the pattern here. Right, x4 star is going to be 4 times 2 over n, x5 star is 5 times 2 over n, and in general, the ith evaluation point is going to be I times 2 over n. Right, that's the pattern. All right, we need to do a real quick sanity check. I equals 1 gives us x1 star. I equals 2 gives us x2 star. I equals 3 gives us x3 star. Yeah. This is the pattern. And this is now what goes in for xi star inside our function. So plugging that in and swapping in 2 over n for delta x, we get the following. All right, now we need to use what our function actually is. All right, our f of x that we plug this into, we need to use what that function is. All right, but our f of x is x cubed. All right, so our function takes whatever we hand it and cubes it. So over here, we're going to get I times 2 over n cubed. Right, this is the point where we had, the first term plus the second term plus the third term plus dot, 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 plus the nth term written in our work yesterday. So the summation notation is a lot more compact. It just takes a little bit of brain power to just remember, that that's what we're working with here. The summation notation means we have a big sum that we're thinking about. All right, but at this point, we can just do some algebra and work with our summation notation formulas. Right, so this cube, right, this is going to distribute over the product and the quotient here. So we can do that. But check this out. This is a little bit hard to see in this form. I claim that there's a constant multiple here. All right, if we look at this term, right, the ith term that we're adding up, right, for I equals 1, I equals 2, I equals 3, all the way up to I equals n. Well, the only thing that's actually changing in this term is this I cubed term. All right, that's going to be 1 cubed, and then 2 cubed, and then 3 cubed. But everything else over here is going to stay the exact same. And so this 2 cubed over n cubed times 2 over n, this is actually a constant multiple. I can do it. Yes, exclamation mark. Okay, constant multiple. All right, and using our constant multiple rule, all right, we can take this and slide it out of our summation notation. There it is. And notice what's left looks a lot cleaner. The sum from I equals 1 to n of I cubed. All right, this is where we were yesterday when we had 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. Right? That's what this sum is. All right, but we know what the sum equals from the formula that we were handed. Right, I'll scroll up just above. And we were handed our formula for what that equals, a nice compact closed form way to write that, without any summation or anything. And so at this point, we can swap that in. N squared times n plus 1 squared over 4. All right, so swapping that in, we get what we see here. And now there's no more summation going on. We just have a nice clean function of n. Now we can just work with our strategy to compute the limit as n goes to infinity. All right, we're going to do a little bit of simplification first, and then we'll pull out the highest power of n in the numerator, the highest power of n in the denominator, and go from there. All right, so to start, let's maybe switch out the n's and the 4 here. Just change their position. All right, n cubed times n is n to the 4th. Now over on the left, our 4, all right, as it did yesterday, will cancel off with 2 of the 2's up top. We'll just get left with 4 out front. And then the n squared will cancel off with 2 of the n's in the bottom. All right, and here I've gone through and distributed out this n plus 1 squared. That is n plus 1 times n plus 1. Just distributing that all out, we get n squared plus 2n plus 1. All right, and now we can out of the whole numerator, right, pull out this n squared. So we'll get 2n over n squared and 1 over n squared up top. And we'll slide out the n squared on the bottom as well. Right, so the n squared becomes 1. 2n over n squared is 2 over n. And we get 1 over n squared. Now our n squareds out front cancel off. And now we can just take the limit of what is remaining. 2 over n and 1 over n squared will both go to 0 as n goes to infinity. All right? And so what we're left with is 4 times 1 plus 0 plus 0. In other words, there's that 4 again. Beautiful. So that's how it can look to use summation notation in our work here. Streamlines what we're writing down and gives us a little bit of cleaner forms to work with. All right, tomorrow we'll get to play around with another example and summation notation a little bit more. That's it for today. Good work, everybody. I'll see you next time.